Okay. Our next talk will be given by David Vegh from Queen Mary, University of London, and it will be about segmented strings in AdS3. So, please. So I will show you.
Can you hear me?
Yeah. So you have 45 minutes, and I will show you fingers.
Okay, great.
Minutes will be like 5 or 10. Please.
Hi, thanks very much for the invitation. I'm very happy to be here in Budapest. I graduated from this university. Very happy to be back after 20 years. Today I'm going to be talking about segmented strings in AdS3, three-dimensional de Sitter space. And first, I think I have to explain to you why I want to talk about this topic. Okay, so I guess very unusually, I'm going to start from the bottom of the slide. Motivation for studying strings in AdS. At this conference, maybe I should not even have this slide. Of course, one huge motivation comes from studying the AdS-CFT correspondence. AdS-CFT in the planar limit, you naturally end up with strings in a fixed AdS background. Okay, you can also think about applications of AdS-CFT if you're like more condensed matter oriented, or if you want to compute Wilson line scattering amplitudes, studying surfaces in AdS also appear. Now, my personal motivation comes from this sentence here. I'm interested in quantum gravity, and I like to understand it. For that, I first want to study toy models for quantum gravity. So it might be worthwhile going down in dimensions, so down to 2 dimensions. Einstein gravity in 2 dimensions is trivial. You can build other models like the Joukhiv-Teitelbaum gravity theory, which has been very popular in the recent years. It provides a low energy sector of the SYK, the Sludge-Vegh-Kitaev model for AdS2. Okay, unfortunately, it does not have local degrees of freedom, so you might want to have a system which does have local degrees of freedom, and the string worldsheet is such a model. Okay, what does it have to do with gravity? My motivation for studying the string came from a series of papers by Shanker and Stanford, where they studied chaos, how chaos appears in AdS-CFT. This is the system that I'm not going to explain now. The bottom line is that they studied out-of-time order correlation functions, 4-point functions. These are hard to compute, very hard to measure, but from them you can read off the Lyapunov exponent, this lambda L here, and that's just a number that you can compute. A few years later, Maldacena, Shanker, and Stanford found a universal bound, upper bound on the Lyapunov exponent, this 2 pi t. There's some h bar in the denominator. Okay, and Shanker and Stanford showed that, and collaborators, they showed that black holes in AdS-CFT saturate this bound. So later, Kitaev showed that the SYK model also saturates this bound. That's what started this mini revolution in 2015. Okay, in 2017, with Jan de Boer, Eva Labres, and Juan Pedraza, we showed that the string worldsheet also saturates this bound. So in that sense, it is similar to Einstein gravity. It has to do with the phase shift when 2 waves cross on the worldsheet. Or you can also look at, in gravity theory, you can look at gravitational shock waves, and you end up with the same phase shift for some reason that nobody understands. Okay, so that's the motivation, but this is all still very complicated, as you know, quantizing the string in AdS, et cetera, et cetera. So what I'm going to do in this talk is I'm going to discretize the string. Okay, so here's the plan for today. First, I'm going to tell you how to discretize the string, what segmented strings are, and then I'm going to show you a few examples. Animations, I wanted this last talk to be fun. Not that the previous talks were not fun. And then this is an integrability conference, so I'm going to, after that, compute the spectral curve in 2 different ways, just to have even more fun. And then after that, I'm going to discuss the simplest example, which turns out to be a string, a closed string consisting of 4 segments. It's going to be still quite complicated, as you'll see. Okay, happy? Everybody happy with this plan? Okay, so here is what segmented strings are. We like to construct segmented strings from straight pieces. Think of piecewise linear strings in flat space. Okay, so here's a straight string. There is a normal vector which is constant, right? So this is what we'd like to see. So how do we put this in the language of mathematics? AdS3, you can embed that into R2, 2, this ambient space as a hyperboloid locally. So it's a 4-dimensional linear space. You need 3 vectors, this embedding vector y, and then you can take derivatives, light cone directions on the worldsheet. So you got 3 vectors, and there is a 4th perpendicular vector to it, which is your normal vector. Okay, so this normal vector is an element of R2, 2. It does not only describe the sort of the direction, the orientation of the string. It also tells you what the transverse velocity of the string is, and also the shift, so where it is in the transverse direction. So this is why I work in AdS3 as opposed to 3-dimensional Minkowski, because you can sort of encapsulate all this information in a nice and covariant way. Okay, so the idea now from 2015 is to glue a big segmented string from pieces which have constant normal vectors. Okay, so I posted this paper 7 years ago, and surprisingly, same place at the same time, Gupser and collaborators also had the same idea. This happens. Okay, so how do we describe a string segment with a constant normal vector? Okay, so here is a picture that I'm very proud of AdS3. And this is the global AdS time direction. And the simplest string embedding is here in green. So it just connects to antipodal points on the boundary of AdS, right? And in these coordinates, it's static embedding. The orange slices are the boundaries of the Poincaré patch. On the Poincaré patch, so here's the boundary. This is the z direction, the radial direction. This green worldsheet looks like, at a given time, like a semicircle, which sort of comes from infinity, shrinks to a minimal size, and then starts expanding again. So that's what it looks like. And you have pictures here how the quarks behave, the string endpoints behave on the boundary. Okay, so this is our elementary string segment. And we'd like to connect 2 of these. Okay, so how do we do that? So if you just arbitrarily connect 2 segments, now here I have pictures of the Poincaré patch. The problem is that you're going to generate bits of the string which move with the speed of light. So that's not good because this has an infinite energy here. So we don't allow that. So there has to be a constraint for adjacent normal vectors, which turns out that the 2 adjacent normal vectors, so for the normal vector for this guy and the normal vector for this guy, these have to multiply to 1. Okay, so that's the rule. And this also implies that this kink here moves with the speed of light. This is, you can understand why that is necessary. It's because if it was any slower than that, you could go to a rest frame locally. But then, obviously, because of the string tension, this could not stay piecewise linear because there is the string does break. Okay, so all the kinks in this talk will move with the speed of light. But they can collide, right? There could be a left-moving kink on the string, a right-moving kink on the string. So eventually, they're going to collide, and you have to handle the situation. What happens when they do collide? So here is a simple, this is really high school algebra. You can go to a frame. So here's a string. You can go to a frame where this line, this string segment is static. This is also static. And this middle one moves upwards with some velocity v, which obviously has to be less than 1. And eventually, these 2 kinks they will collide up here. So you can convince yourself that the only thing that can happen is that v goes to minus v after the collision. So there's sort of a time reversal symmetry here. And after the collision, the string segment starts to move downwards. And you can look at this from the point of view of the normal vectors, how the normal vector A corresponding to this middle segment changes. And there is this reflection formula, which kind of tells you what happens. So you have to reflect this normal vector A on like sort of the average of the other two normal vectors. Okay, so let's see how this works in practice. So I'm going to show you a few animations, and then we get back to integrability. Okay, so here you see 3 segments on the Poincare patch. This is segment 1. This is a middle segment here, segment number 3. And after the strings kinks collide, you see the normal vector changes, and this middle bit leaves this, this dashed line here. Okay. Let's see the next one. Okay, you can do some crazy things in global AdS. You can generate lots of kinks, and at the end of the talk, you'll be able to compute the spectral curve for these guys, well, closed versions of it. You can also, so as it turns out, segmented strings can approximate any smooth string to arbitrary accuracy. So this is a dense set in the space of string solutions in AdS. So here I'm approximating this dashed line, which is given by some elliptic integral. So there's just a string hanging from the boundary of AdS, and I'm approximating it with this complicated string, which contains lots of kinks moving with the speed of light. So that sounds a bit silly. Why do I do that? It's because after that I can do this. So this, now you don't see the individual segments. There are like 500 segments in this animation. So you can perturb one of the endpoints. After the quench, there's a large wave that's created, and you can study things like wave turbulence using this integrable model. Okay, so I cut off the animation at some time, but this can go on for an arbitrary time because it's an exact solution to the Nambu-Goto string in AdS3. All right, so let me go back to the talk, if I can find it. Thanks. Okay, so how did I do this, especially the last animation? I have to go back to this. Unfortunately, if you try to just implement this reflection formula, this kind of exponentially increases the tiniest numerical errors. So it's not good because computers store real numbers as rational numbers. And after a few hundred reflections, those tiny errors get blown up, and you end up with a mess. So there, I found a different description, which I'm going to tell you about now. Okay, so this brings us to this topic of celestial variables. This is all related to Andy Strominger's story, except they work in Minkowski spacetime, and I work in R2,2. Okay, so maybe the letters are tiny, but I'm just gonna tell you the main story here. So let's look at the worldsheet. So how do we quantize? How do we discretize the string? Here's a worldsheet, and these lines here are the kink world lines. So as I told you, they move with the speed of light, so these are 45-degree angles. Okay, so the vertices are this V0, V1, etc. These are all in points in R2,2. Okay, so you can subtract them from each other. It's a linear space, so I can just generate these P vectors. And then, if you rotate these by 90 degrees, you can think of this diagram as a Feynman diagram. Okay, so what is the action of the string? Well, the action is just the area of this diamond. So for dimensional analysis, this area can only depend on the ratio of these two Mandelstam variables that you can build from these P difference vectors. And in some nice and symmetrical case, you can actually do the integration and figure out that the function is just log of u over s squared. Okay, so that's the area. Now these P's, these kink velocity vectors are null vectors in R2, 2 because the kinks move with the speed of light. So now you go to the spinor helicity formalism and you build these P vectors as a product of two spinors. These are two component spinors and they are real because we are in R2, 2. Okay, so in terms of these lambda and lambda tilde vectors, you can write down this area. And using the fact that these four lines have to close, momentum conservation, you can eliminate the lambda tildes from the formula, and you end up with this kind of cross ratio looking thing in terms of the lambda variables. Now you see that lambda 1 appears upstairs and also downstairs, and same for the others. So you can multiply the spinors by a number, and that drops out. So in fact, only the angle or the ratio of the two spinor components will matter. Let's call them celestial variables. So you have the two component spinor, and I just take the ratio of the two components. And I'm going to call these A numbers, celestial variables. In terms of the original difference vector, it's a formula like this. Okay? If you're familiar with the celestial sphere story, then there's an I in that story here in front of P2. But in this talk, everything is real, except for perhaps the spectral parameter. Okay, so in terms of these A numbers, you do get a cross ratio. So that is the area of the string worldsheet for this patch. Okay, just to summarize, we went from the vertices, we computed these difference vectors, we decomposed them into a product of two spinors, and the spinor component ratios are the celestial variables. And these A numbers sit on the edges, the kink word lines. So one kink word line, one celestial variable. So what's the next step? Well, we add up the areas of all the patches. So you compute the total action. You compute the total action, you have the action, you can derive the equation of motion for these A variables, the celestial variables. And this is what you get. Okay, so here is the worldsheet again with lots of patches. And I put here these white and black boxes so that you can see that they form a square lattice. Okay, and when you compute the equation of motion for the celestial variables, this is what you get. It's a known integrable model. Oops. It's a nonlinear model, so not entirely trivial. Okay, so what if you have all these celestial variables, you solve the equation of motion. How do you reconstruct the string embedding? Well, it's not too complicated. So here is the artist's impression of a worldsheet. And there are some kink lines here denoted by these black lines. And I sort of unwrap it, and I show it here on the right-hand side as well. So if the enemy gives you these two rows of celestial variables, this guy here, this, that, etc., and the enemy also gives you the P point, you can compute the normal vector of this adjacent AdS2 patch using some not too complicated reflection matrix. So remember, P is a vertex in R2, 2. You multiply, you apply this 4x4 matrix on it, and you get another 4 vector, which is going to be your normal vector. And then you can do this procedure again from N1, this normal vector, you can compute this Q point using these two celestial variables. And so on, you can continue the procedure, and you recover the entire string embedding. Okay, so surprisingly, or maybe not too surprisingly, just by knowing these celestial variables, you can reconstruct the entire string embedding up to a global SL2 transformation. In the smooth limit, these two, the black dots and the white dots, they become two different smooth fields on the string worldsheet. All right, so now we know how to generate those animations I showed you. Let's talk about something else. So I'm going to tell you a simple brute force way how to compute the spectral curve, and then I'm going to tell you it in a different, more exciting way. Okay, so using the Pohlmeier reduction, you can massage the equation of motion, and then you end up with the generalized Hinch-Gordon equation, which is written here. Okay, for this equation, the flat connection is known. I just copied some equations from this paper by Alday and Maldacena, 2009. And you define an auxiliary linear problem. So this psi is a two-component spinor. And if you solve this spinor, these spinor equations, from the solutions you can reconstruct the string embedding. So in general, it's very hard to solve these equations, of course. But we are dealing with segmented strings, and the elementary segments are very simple, like AdS2 patches, basically. So you can, in fact, you can solve these equations. So here's one patch, bounded by the kink word lines. And you can solve the spinor equation here, and you'd like to connect it to some other spinor solutions and build the global spinor frame. Okay, so what it turns out that you have to connect it to another spinor solution, which is is valid in the vertex region. I blew up this dot here, which is now this orange region. That's the kink. That's the vertex region where the embedding function does not change, but the normal vector changes. Okay, so you can also solve a similar equation here. You get the spinor solution here in the orange region. You have it in the AdS2 region. And then using some matched asymptotic expansion, you can connect the two solutions, and you can figure out what the Lox matrix is. So you end up with this 2x2 SL2 Lox matrix, and zeta here is the spectral parameter. You can either do this, or you can just look at the book by Suris and discover a very similar matrix. All right, so from these Lox matrices, you can build the monodromy for a closed string. Just basically multiply these matrices and their inverses. And in every matrix, there are two celestial variables which enter. So you can actually write down the spectral curve in terms of these celestial variables completely explicitly. Now that's not all of the story, because these celestial variables are not completely arbitrary. There are some constraints, because if the enemy just gives you 2n celestial variables, then the string won't close. So you want to avoid this kind of situation. There is a constraint, a global constraint, which forces the string to close. And that turns out that it's equivalent to this constraint. Some special point, this omega monodromy matrix has to be trivial. Okay, so this gives 3 real constraints on the celestial variables. All right, so that's the brute force way. And now here's the exciting way of computing the spectral curve. And it's especially exciting to me because it connects with my old work on brane tilings from 2005 and 6. Okay, raise your hand if you know what a brane tiling is. Oh, 1%. Excellent. 2. Good. Okay, so what is brane tiling? It's a doubly periodic bipartite graph. So the fundamental domain is indicated here by this red rectangle. So the tiling, you can think of it as a planar graph drawn on the surface of a torus. Okay, so we used these objects back in 2005 with Ami Hanani, Seba Franco, and others to encode the Lagrangian of n=1 supersymmetric gauge theories in 4 dimensions. The dual graph, the graph theoretical dual, is the quiver of the theory. And interestingly, the tiling also encodes the terms in the superpotential. So these black and white dots are going to be terms in the superpotential. And this is also related to the story of these people on on-shell diagrams, right? Except that in this case, the tiling is, it's on a genus 1 surface, not planar. Now, it's often said that the best invariant of a graph is the graph itself. So that's true for generic graphs, but for this particular planar doubly periodic graphs, you can in fact find an invariant object. And it's basically you take the adjacency matrix of the graph, and you compute the determinant. So you get some polynomial in 2 variables, and the Newton polygon is drawn here on the right-hand side. Now, there are transformations you can apply on the tiling. So this one is a famous one. This has at least 10 different names: urban renewal, spider move, Bosnikov move, square move. We call it a Seiberg duality in the context of n=1 theories, which is an infrared duality. And there is another move where you eliminate valence 2 vertices. And the invariant object it remains the same. So the Newton polygon does not change. Here's a little bit more concretely the calculation for this particular tiling. So you assign weights to the edges which cross the boundary of your fundamental domain. So x inverse depending on the orientation, and y here which crosses the vertical boundary. And you build the adjacency matrix, which in this context is called the Castellane matrix. Okay, so the rows and the columns are labeled by the black and white vertices. So there are 6 vertices, 3 black, 3 white. So this is a 3 by 3 matrix. And you see, for instance, the 1, 3 component is 0 because the white 1 is not connected to black 3. But the white 1 is connected to black 2, so I put a +1 here. There are also some signs that I'm not going to explain. Okay, so that's the Castellane matrix. You compute the determinant. You get a Laurent polynomial in 2 variables, which then gives you this Newton polygon. Interestingly, you can go from this Newton polygon back to the tiling. I mean, at some point you take a determinant, so it's a bit unusual that you can do that. I found a very nice graphical way to do this back in 2005 with Ami Hanani. You don't get the tiling uniquely, you get it up to these transformations that I showed you. All right, so about 10 years ago, Gončarov and Kenyon told us that there is a corresponding quantum integrable model to almost every tiling, and the dynamical variables are oriented edge loops in the tiling. So for instance, this edge loop here. Or you can go around the face, so that's another edge loop, and that will be a dynamical variable in your system. So these face edge loops are denoted by Fi. This form a basis for all the dynamical variables. And in the Gončarov and Kenyon story, they satisfy quadratic Poisson brackets. This can be quantized. Unfortunately for us, for the string sigma model, we don't get quadratic Poisson brackets. For the string in AdS3, I'm not going to talk about that, but these are quartic brackets that we are interested in. But no matter, the equations of motion are the same. So we can try to embed the motion of the segmented string into these systems. So how do we do that? So I like to look at I want you to look at the worldsheet again. So here are the kink lines. This is the tau direction. This is the sigma direction on the worldsheet. You can think of sigma as being a compact direction, so we study a closed string. And think of it as an on-shell diagram. So here where two kinks collide, like, oh, the mouse keeps jumping. This point here, or that point, or this point, you can think of that as a sort of composite vertex. So blow it up. So that's what I did here in the middle figure. I added these tree-level diagrams, these squares, and you can imagine that they are growing now. So you collapse these two black dots, these two white dots, these two and these two, etc. So you end up with a square lattice. Okay, it's periodic in the sigma direction, and it's not periodic in the tau direction. This is not the brane tiling. This is still just an on-shell diagram. To get to the brane tiling, well, it already suggests that you are going to end up with a square lattice. So instead of tau, you want to pick an auxiliary direction. And this is what I'm showing you on the right-hand side. So the horizontal axis is still related to the sigma direction on the string. So you go around the string. That's this horizontal direction. But this vertical direction, this is going to be always 2 square tall. This is the auxiliary direction of your spectral curve. Okay, so this is the brane tiling. For a segmented string with n segments, it's a 2 by n square lattice and doubly periodic. Okay, so how is this related? And I can just color these faces with 2 different gray colors, because these 2 face variables, dynamical variables, sort of mean different things. So how are these dynamical variables related to the celestial variables that I talked about? Well, it turns out that they can be given by cross ratios. So these p's especially are just simple cross ratios of nearby celestial variables on the worldsheet. The indices don't look at the indices. It's not important. The Q variables are slightly more complicated cross ratios. What's important is that these are Möbius invariant. So sort of the isometric group of AdS3 is gone now if you look at the brane tiling. Now you can start to perform cluster transformations. These are the urban renewal transformations, and you can figure out how they act on the dynamical variables P and Q. And this is what you get. So you see that the P and Q variables form a Y system. And then you can check explicitly that these are compatible or equivalent to the original equation of motion for the celestial variables. Okay, so we managed to embed the motion of the segmented string into the cluster transformation dynamics of a brane tiling, this particular brane tiling. And it's very easy to compute the spectral curve because you're going to want to just compute the determinant of the adjacency matrix, the Castellane matrix, and you have the spectral curve in terms of your celestial variables or these P and Q variables. All right, so let's have a look at the simplest case. I don't have an animation for this. You can just sort of move your head left and right. So this is these are snapshots of the string, and it sort of just oscillates between these 2 positions. This string is characterized by 2 numbers, the length of this line here and the length of that line here. Yes?
One question on the previous slide. Can I see regarding the control's argument of integrability?
Which argument?
Control.
Yes.
On the integrable system. Can I see it as having always a dual
mean, it depends on what you want to do with the dual quiver.
Yeah, probably such that the quiver at least
Yeah, I did not think about that. Yeah. All right, so just back to this picture. So this string is characterized by two numbers, these two lengths. And if I were to set this length to 0, that's a very special case, then you just have basically two endpoints moving on a subspace like that, connected by a string. That's the simplest folded string, and it only has longitudinal degree of freedom. Okay, so here's the calculation. It is really very simple. Here's a picture of the string again, and here's the worldsheet. And these two dashed lines are identified. So this is the tau direction, that's sigma. And this P point is the same as that P point. And on a generic time slice, you have 4 kinks or 4 string segments. And on the right-hand side, you see the brane tiling. It has 8 squares. And now you can compute the Castellane matrix. So you can compute the spectral curve in 2 different ways. You can either use those omega 2x2 matrices, lux matrices, and multiply them, and then build a spectral curve like that. Or you can just compute the determinant of the Castellane matrix. And you get the same thing. You get this result where x and y are the 2 weights when you cross the edges, or the boundaries. And delta is the space-time energy of the string. Okay, so delta is the space-time energy of the string, which is related to the 2 lengths characterizing the string. So they do not appear separately. This also means that from the spectral curve, you cannot reconstruct the string embedding completely uniquely because you've lost information. Okay, so you have x and y, that's your spectral curve. But I'm now going to define some other spectral parameters. In fact, there are 4 different spectral parameters on this slide. I'm sorry about that. There is this zeta, and I think zeta squared is x, and x is related to the Zhukovsky x like this, and then you can define this u spectral parameter from the Zhukovsky x via this formula. And finally, I rewrite y as e to the p. And then you go to the thesis of the previous speaker, and you learn that p and u are canonically conjugate variables. So in terms of p and u, this is your spectral curve. It's very simple. And I defined here this g, some coupling constant. Okay, what else do I want to tell you about this? You can also express delta, the energy, from this equation. And this is what you get. So if you're familiar with the Reisenauer-Schneider theory, you get something that looks like that, except you don't have the Weierstrass P function in here. You have something simple. And this H is not, it does not generate the Poincare algebra. It's part of the an SL2 algebra that's more appropriate for AdS2 or AdS3. Okay, so here, this is now where I would turn to quantization. Unfortunately, that's work in progress. So this is my last slide. So I can spend 4 minutes on this slide. It needs more than 4 minutes, I can tell you that. So here is the spectral curve again. And as I told you, the spectral curve does not depend on the squashing parameter. You can compress the string completely, and you end up with 2 endpoints connected by a string. So you squash the string, and you can also go to the flat space limit. Who cares about AdS3? Go to the flat space limit, so you really just have 2 sort of quarks connected by a string. And in this limit, the quantization probably should be given by the 't Hooft equation. So the 't Hooft equation, the 't Hooft model, well, if you've never seen this paper, you should read it today. It describes meson band states in planar 2-dimensional QCD. So this phi of x is the wave function, and x is the momentum fraction, the Bjorken x. So this p is the capital P is the total momentum of the two quarks. So you boost the two quark system, and p1 is the momentum of one of the quarks. Okay, so x is just the ratio. And the other quark has momentum fraction 1 minus x. Okay, so then this integral equation describes the wave function. Alpha 1 and alpha 2 are some renormalized masses, mass squared numbers here. You can set them to 0 here for the purposes of this talk. And now you can switch to rapidity coordinates, this theta given by this expression, and do a Fourier transformation. And then you end up with some 5 new function, still an integral equation, but you can turn that into a difference equation. So a simpler version was already in this paper by Brouwer, Spence, and Weiss at the end of the 70s. But this particular equation I've seen in this paper by Faddeev, Lukyanov, and Zamolodchikov in 2009. So they end up with this equation. And looks complicated. What does it have to do with this equation, or classical spectral curve? Well, since this system is very simple, you can also just compute the Hamiltonian and everything by directly looking at a folded string in AdS3. And if you know a little bit about the Reisenauer-Schneider model, you can figure out some canonical transformation between this P and U variable and those more natural physical variables, like the quark locations in AdS3. So you can actually relate this U, you can figure out the configuration space exactly. And it turns out that this region, which in some other models is the Joukowsky cut, this is not part of the configuration space. So only U larger than 2G or U less than minus 2G is part of your configuration space, so you might want to cut this out. Okay, so you can define some U tilde variable where you sort of take this middle region and you cut it out, and then you glue your space, your real line, U line, back together again. So that's what this U tilde is. And in terms of this U tilde, you get a weird looking equation, which obviously has an absolute value in it. So I'm just going to let you now compare this equation and that equation, and compare this tanh nu over nu to this 1 over U tilde absolute value. So maybe you can think of the Toft equation as a very simple quantum spectral curve, which works slightly differently because you cut out a region. Okay, I think my time is up, so I'm just going to leave you with this summary slide. So we studied a bosonic string in AdS3, and using exact discretization, we reduced it to a model with a finite number of degrees of freedom. And we computed the spectral curve using brane tiling technology and some other brute force way as well. And there are some questions, how to quantize these objects. Well, in the flat space limit, this is what you should get from the previous slide. This would be super useful if you were to really study quantum gravity. Now, you might run into difficulties, so you might just want to go to AdS5 cross S5 instead. So how to generalize this to AdS5 cross S5 is still unknown. And a final question is, if you really think about the string worldsheet as a model for gravity, the question is, does it have a holographic dual, some kind of 0+1 dimensional theory, maybe a matrix model? And again, I don't know the answer to this. Thank you.
Thanks a lot for a very nice talk, David. Please, questions? Kola?
Hello. Thanks for the nice talk. Can you have a version of this on S3 rather than an AdS3?
A version on?
for string on S3 rather than on AdS3?
S3.
Yes.
Excellent question. I tried to do that. I failed. I suspect it should work in some ways, but I don't yet know how. I think it's easier to generalize it to AdSN. S, I don't know. The problem with exact discretization is that there is no algorithm to do that, right? So it's easy to go to the smooth version from the discrete version, but not vice versa.
More questions? I wanted to ask you something. So you get something like R matrix here, yes? For could it
I
be
only told you
called-
about a system with 1 degree of freedom, like at the end. The R matrix, I don't know. I have not looked at it yet.
But if you have,
I don't know if it's a quantum integrable model
if
or
you
not.
have a few degrees of freedom,
That's what you want, yes.
do you feel it's integrable also? So there is no clue yet what kind of
It's unclear. Classically
which
integrable. Yeah.
integrable model you can map it. Sounds, many elements sound very familiar to integrability.
Classically, it's integrable, but quantum story, I am not sure.
No, okay, even classically, I mean. Okay, thank you. So, if there are no more questions, let's thank again David.